An alkane is called a saturated hydrocarbon. So we're talking about alkanes. And it's a hydrocarbon, which means it's only comprised of carbon and hydrogen atoms. It's saturated in that it only has single bonds. So an alkane has a general chemical formula of CnH2n plus 2. And you see all of the chemical formulas down here follow that generic or general chemical formula. When you name an alkane always has the ending ANE. See, this is ANE on all of these names. Now, some of these names I used in a previous video, but now we're going to explain where they come from. Methane has one carbon. It's the simplest of the hydrocarbons, and meth is the prefix used to tell us that we have one carbon. Eth is the prefix used to tell us that we have two. Prop is 3, bute is 4, pent is 5, hex is 6. Then we continue on with Greek prefixes. We have sept for 7, oct for 8, non for 9, dec for 10, and it continues. We could go up pretty far, but here's an example. Octadecane is 18 carbon atoms. Now you see here is an alternate condensed structural formula. And we have an H, and then we have a CH2 group, and then another H. And you see we've continued that through this table, CH2 groups, and you see the CH2 groups increase as you move down. And that tells us how many carbons we have as well. So these CH2 groups are called methylene groups, methylene. And when you have this series, when you have a series of chemicals that only differ in the number of methylene groups they have, this series is called a homologue. Now, when we have these chemicals, and we can use a skeletal structure in order to show these chemicals. So methane, we don't really have a skeletal structure for, but ethane was just the line. Remember, a carbon at every end and bend. There are two ends, two carbons. So that would be propane, that would be butane, pentane, hexane, heptane, octane, etc. And we could keep going. We just keep zigzagging up and down. Remember, there's a carbon at every end and bend, and the hydrogens are implied. Carbon wants to make 4 bonds, so we could just keep going. But you get the idea. We have these straight chains. So whenever you have a straight chain alkane, these are called your N-alkanes. When you take off one hydrogen from an N-alkane, what you form is called an alkyl group. Similar to the alkanes, we have a pattern. And that pattern has the root of the number of carbons we have, and then we have a new ending. So we have a YL as the ending. And that tells us we have what is called an alkyl group. To show just a generic alkyl group, we don't know what it is, we just know that there's more molecule to it, we use an R. R is the symbol for a generic alkyl group. Now, all of these alkyl groups, or these 3 alkyl groups that I specifically highlighted, they remove a hydrogen from one of the terminal carbon atoms. Well, in methane, there is no terminal carbon atom. It's only the one atom, but you get the idea. Now, in order to move forward and name some of the other groups that were given there, we need to understand the order of our carbons. And that doesn't mean how they're bonded or who comes first or second. When I say the order of the carbon, I'm talking about what's called a primary, secondary, tertiary, or quaternary carbon. And that order tells us how many other carbon bonds there are. For example, if I'm looking at this carbon here, this carbon has one carbon-carbon bond. Therefore, this is a primary carbon. going to change my color briefly. So this carbon has 2 carbon-carbon bonds. There's this one and there's this one. So this is a secondary carbon. So if we can find a carbon that has 3 carbon-carbon bonds, we would have a tertiary carbon. So I'm going to look at this one here. So I have a carbon-carbon bond here, here, and here. So that is a tertiary carbon. Now there is a carbon heteroatom bond here that doesn't factor into the order of this carbon. Now we can also have what are called quaternary carbons. And a quaternary carbon, I'm going to use green, will have 4 carbon-carbon bonds. Now a quaternary carbon does not have a hydrogen bonded to it because it has 4 carbon-carbon bonds. Now, like carbon, our hydrogen atoms can be primary, secondary, and tertiary. You will not have a quaternary hydrogen atom. And that's because the order of the hydrogen atom is related to the carbon that it's bonded to. So these hydrogen atoms are primary hydrogen atoms because they're bonded to a primary carbon. These hydrogen atoms, let's see, I'm going to have to erase this one. These hydrogen atoms here are secondary hydrogen atoms because they are bonded to a secondary carbon. And similarly, well, if this was a hydrogen, then it would be a tertiary hydrogen, but we don't have a tertiary hydrogen in this molecule. So that's what we're talking about when we're talking about the order of an atom. It's how many carbon-carbon bonds are there, at least for our alcohol groups, carbons, and hydrogens. So when we remove a primary hydrogen, if we have butane here and we remove this primary hydrogen, then we have, this would be N-butane, then we have what's called an N-butyl group. Well, if we have an isomer, remember an isomer is where we can take the atoms and we can arrange them in a different way. This is butane, but this is called isobutane. What happens is we have this tertiary carbon that is created. And when we remove one of the primary hydrogens off of isobutane, then what we form is called isobutyl, an isobutyl group. If we remove a secondary hydrogen, change my color here. If we remove a secondary hydrogen, that would be one of these from butane, then we have a new prefix that we need to add to it, and that is a sec. So we add sec to say we've removed a secondary hydrogen, butyl. So now I have a sec-butyl group. So when this group attaches to something, it's going to attach at this point right here. That's a sec-butyl group. You see that denoted right here. If I remove the tertiary hydrogen from isobutane, so if I remove this one, then what I've formed is called a tert for tertiary butyl group. And then this group would attach, if it's going to attach somewhere, it's going to attach right here on the tertiary carbon. So that's how we get some of our special names, and that's how we get some of the special groups that were noted up here. The iso, sec, and tert. That's where those come from. When you go to name alkanes, you always start by finding what's called the main chain. Sometimes it's called the parent chain or the parent hydrocarbon. This is going to be the longest continuous chain of carbon atoms. So, and it might go around a corner. So you might need to try to number it a couple of different ways. Now there could be more than one chain that is the same length. You're going to use the chain that has the most number of substituents for your main chain. You're then going to number that chain, and you're going to begin with the end that's nearest a substituent, and you're going to number the carbons of that chain. And the idea is to have the lowest number possible. You're then going to name your substituents, You're going to put them in alphabetical order. You're going to find the number associated with the substituents that gives you the address of where to find them. And you're going to organize everything together and name your compound. So let's start with something that looks like this. So this compound, we would start by numbering our chain. You see there are 8 carbons here. Now I could have started my numbering, let's change my color just to show you something different. I could have started my numbering here. And if I had done that, then I would have only had 7 carbons in my chain. And that would be incorrect, because if I can number it a different way and get a larger number, then that's the number I need to use. So here I have 8 carbons in this chain. That means I have an octane. Now I need to organize my substituents. I have this substituent here. This is called a methyl group. You see there's a carbon right here at the end, carbon at every end and bend. So this is a methyl group. And this methyl group, now I need to give it an address. I'm going to put my methyl here. The methyl group is located on carbon 3 of my chain. So this is called 3-methyl octane. Now let's try another one. What would this group be called? Well, if you remember from earlier, this was called isobutane. But what if we name it using the rules that we have now? These rules are called IUPAC rules. IUPAC is the international, and then there's something French, but it's an international method of systematically naming our organic compounds so that we always know what we're talking about regardless of where we are in the world. So we name our longest, or we number our longest chain. You see, I have 3 carbons here. Well, what if I was to go this way? That's okay too. This is an example of having more than one way to number the parent chain the same. So I have 3 carbons, which means I have a prop. And I only have single bonds, so it's propane. Then I need to organize, number, and name my substituents. I have a methyl group, and my methyl group lives at carbon 2. So this is 2-methyl propane. Well, what if we were to go the other way? What if I were to tell you that we had 4-ethyl nonane and asked you to draw that molecule? First, draw a 9-carbon backbone. So here's 2, 4, 6, 8. I think I did 10 there. So there's 9 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9. Remember, there's a carbon at every end and every bend. And then at carbon number 4, I need to put an ethyl group. Ethyl tells me that I have a 2-carbon chain. So at carbon number 4, I'm going to give it 1, 2. So this is 4-ethyl nonane. Well, now I'm going to change it a little bit. I'm going to add another substituent. And when I add that other substituent, I'm going to add it right here. And I'm going to give it a methyl group. Now, I still have nonane, but this time I need to start my numbering here. And I'm going to number using this blue, and then I'm going to number the other way using this pink color to show you why. So using the pink numbers, I have an ethyl that lives at 4, and I have a methyl at 7. Now using the blue numbers, my ethyl is at 3, and nope, I'm wrong. My ethyl is at 6, and my methyl is at 3. Because 3 and 6 are smaller than 4 and 7, we're going to use the blue numbers. So you have to pay attention to where all of your substituents are and look at everything as a whole. So it's still nonane, but now we have a methyl at 3 and an ethyl at 6. But we need to put our substituents in alphabetical order. So this would be 6-ethyl, because E comes before M, 3-methyl nonane. Now, if I add another substituent, and I just so happen to put it there, now we're going to change it just a little bit. So my numbering is going to stay in the same order, but now I have another methyl group at number 3. And I need to indicate that by, instead of just having methyl, now I have a 3,3 dimethyl. Every substituent gets a number, even if it's the same as something else. The prefixes, the di, or if you have 3 of something, it would be tri. The sec or tert that would be used to describe the secondary or tertiary hydrogen that was removed, they do not get alphabetized. They are ignored, and you only use the root for alphabetical order. So although D comes before E, we're ignoring the purple di, and we're using the eth and the meth in order to put everything in alphabetical order. So let's try one more. If I have a 3,3 dimethyl hexane. First, start with your root. You have a 6-carbon chain. You have 2 methyl groups, and they both live at carbon 3. 1, 2, 3. Well, what if I numbered the other way? 1, 2, 3, and I put my methyl groups there? Well, the reality is these are equivalent. These are the same compound, because all you have to do is flip it over, and you have the same compound. So that is naming alkanes with substituents. Now we can also have alkanes that form what are called rings. They are cyclic compounds, and we name them by putting the word cyclo in front. All cycloalkanes will have the general formula CnH2n. That's for saturated cyclic alkanes. You see that formula right here. And as you can see, if we have a 3-carbon chain, that's called cyclopropane, and it looks like a triangle. A 4-carbon ring is going to be called cyclobutane. It looks like a square. Cyclopentane happens to look like a pentagon. Cyclohexane looks like a hexagon. Cycloheptane looks like a heptagon, etc. Now, naming these is very similar to any of your straight chain, your N-alkanes. The difference is in how you're going to number. So if you have something like this, and you'll see a lot of 6-membered ring structures in organic chemistry, and let's say you have a substituent here and you have a substituent here. Let's start with the same rules. We have a 6-membered ring here, so we would call that cyclohexane. That's my parent. And then I have substituents at this carbon, and I have substituents at this carbon. So I'm either going to number it this way, so we'll go inside numbers, or I'm going to number it this way, outside numbers. Now I have 2 substituents on this carbon, so this would either be carbon 1 or 3, and I have 1 substituent here on this carbon, which would again be either carbon 1 or 3. Now we want to decrease our numbers, and since 113 is less than 331, we would call this 113 trimethyl cyclohexane. So what if we had something like 2-bromo 3-chloro 1,1-dimethyl cyclohexane? It looks like it's going to be a really big molecule, but you just follow the same rules. Start with your root, your parent chain. You have a cyclohexane. And just because I need to start somewhere, I'm going to call this carbon 1, 2, 3, 4. I'm just going to number it that way. 1,1-dimethyl. So that means I have 2 methyl groups on carbon 1. 2 gets a bromo. That's bromine. 3 gets a chloro. So I put a chlorine there. So all of this becomes this structure.